In the previous video, we talked about how we can use our solubility rules to predict the phase of products and reactants in chemical reactions that involve ionic compounds. In this video, we're going to take this idea one step further and figure out what ions are important in the physical chemistry that's happening and which are not. So let's start this by looking at the balanced ionic reaction that we saw in the previous video between silver nitrate and sodium chloride. We established that in this reaction we form a solid, silver chloride. Okay, so we can break this down into individual ions. So anytime we have an ionic compound that's aqueous, remember how we talked about aqueous ionic compounds get dissolved in water because water surrounds them. So in water, any ionic compound that's aqueous is actually broken up into its ionic constituents. So silver nitrate in water does not exist as an ionic compound. It exists as a silver cation and a nitrate anion. Sodium chloride is aqueous, so it does not exist as sodium chloride, but instead it exists as a sodium cation and a chloride anion. Sodium nitrate is also aqueous, so it exists as a sodium cation and a nitrate anion. Right? So it's broken apart into its ionic compounds. But silver chloride is a solid. So in water, silver chloride does not break apart into ions. Instead, it remains as a silver chloride solid. Okay? And this is kind of key to identifying a new term we're going to call spectator ions. So when we look at this reaction, what we notice is that we have some ions on each side of the reaction that look identical. We have a nitrate anion on the left side, on our reactant side, and we have a nitrate anion present on the product side. So nitrate, in this case, really isn't doing anything, right? So nitrate is present on both sides, it's not doing anything. Sodium is present on both sides. It's not doing anything. So we call these spectator ions. So we'll write that up here, spectator ions. They look identical on both sides of the chemical reaction, reactants and products. They're not participating in the chemistry, but they're watching it happen. So they're spectating. It's like watching a baseball game or watching a football game. You're there, but you're not doing anything. Okay, silver, all right, so silver and chloride, however, do not look the same on my reactant side and the product side. On the reactant side, they are present as a silver cation and a chloride anion. And on the product side, they're present as a solid silver chloride. So we can simplify this reaction where we eliminate spectators. The only chemistry that's happening that matters is between the silver cation and the chloride anion. And these combine together to make the silver chloride insoluble ionic compound. So this reaction is known as our net ionic reaction. It's the chemical reaction that's happening that matters. We've eliminated all the spectators and we're looking at the chemistry that's actually physically happening. Let's apply this idea to our other example we saw in the previous video between lead acetate and potassium carbonate. So we'll go ahead and scroll this a little bit further up. So our goal here is to identify spectator ions and then write out our net ionic equation. Okay, so let's start off by identifying our aqueous ionic compounds, and we'll break them apart into the individual ionic components that are present in water. So we have a lead cation. I have two acetates, so I have two equivalents of acetate. I have two potassiums. I have one carbonate. I have two potassium acetates, right? So two potassium acetate. So I have two potassiums and 2 acetates. And now I have my solid insoluble lead carbonate. So PbCO3 is still together as a solid. So in this case, I can quickly pick out my spectators. I have 2 acetates present on both sides, and I have 2 potassium cations present on both sides. They look the same on both sides, so these are my spectators. So my spectator ions are potassium and acetate. So in this case, the net ionic equation, the net ionic reaction, occurs between the lead cation, the carbonate anion, and we form a solid lead carbonate. And if you do this properly, this net ionic reaction should come out balanced already, because you started with a balanced reaction, so your net ionic equation should also be balanced.